All right, hello everyone. Welcome to lesson 24. So lesson 24 is all about curve sketching or graphing functions by hand. Now, this is going to combine many of the lessons that we've learned about the past few videos. So it's going to take into account the first and second derivative. We're going to need to define mins and maxes, where it's concave up or down, and where it's increasing or decreasing. Now, some of you out there might be wondering, why do we care about curve sketching in the era of the internet or graphing calculators? And the answer is the act of curve sketching ends up telling you a lot about your function. In order to graph the function accurately, you need to know all of the things I just mentioned, where it's increasing or decreasing, where it's concave up or down, where its mins or maxes are, and those are often useful pieces of information. So essentially, curve sketching is giving us practice analyzing functions. All right, so all of these functions are going to be different from each other, but the algorithm we're going to use to graph them will be the same every single time. The first thing that we're going to do is we're going to find asymptotes and end behavior. So remember, end behavior is what a function does as x goes to infinity or negative infinity, and we can have vertical and horizontal asymptotes. So these will be important features of our graph, and we find these by looking at the formula for the original function. Next, what we're going to do is we're going to find all of the function's critical points and local mins and maxes. And to do this, we're going to use f prime of x. Next, we're going to, oh, I suppose we're also going to find out where it's increasing and decreasing as well. I forgot to mention that bit. All right, now for the third step, we're going to find inflection points and concavity, whether it's going to be concave up or concave down in certain regions. This will be f double prime of x. So we need to know about the function, its derivative, and its second derivative to get an accurate graph. Okay, next what we're going to do is we're going to combine the information we found into a number line. And I'll show you how to do that once we approach some of the examples. Step 5, this is where we're actually going to begin plotting the graph. So steps 1 through 4, we were finding out information. Step 5, we're actually going to plot the graph. So the first thing we should do is plot, and I'm going to put this in quotes, important points. So these points could include mins or maxes or inflection points or even x or y intercepts. The more these points we plot, the more accurate our graph will end up being. And then finally, we're going to connect the points with what I'm going to call basic shapes. So there are going to end up being 4 of these basic shapes, and I'll get to these once we start doing the example. But then once we connect the points with these shapes, then we actually have a complete graph. So that's what it's going to be. And unfortunately, this process can take quite a while because we need to compute 2 derivatives, do a bunch of algebra in these steps, and then we have the actual plotting part. All right, so let's go ahead and get some examples going here. Let's say we have the function f of x is x minus 2 squared times x plus 1. And we want to sketch the graph of this function. All right, well, step 1, we're going to find the asymptotes and end behavior for this function. All right, so if we were to FOIL all of this out, this would be a cubic polynomial with a positive leading coefficient. So this means that the limit as x goes to infinity of our function will be positive infinity, and the limit as x goes to negative infinity for our function will be negative infinity. Because cubic polynomials, they always look something like They typically look something like this. And this is one with a positive coefficient. So we're going off to infinity this way and then down to negative infinity this way. All right, so this is the end behavior. And since these were both infinite, we don't have any horizontal asymptotes. So horizontal asymptotes come from when these limits are finite numbers. And then we also have no vertical asymptotes because we're not dividing by 0, or we don't have log of 0 or tangent of pi over 2 or anything else that can give us a vertical asymptote. And in fact, that will never happen for a polynomial. So this function doesn't have any asymptotes whatsoever. All right, next, let's go ahead and try to find our critical points. So our critical points occur when our derivative is 0 or undefined. First, let's find our derivative here. So there are two ways of doing this. We could FOIL all of this out first and then do the power rule on every term, or we could do the product rule as it's written. I'm going to do the product rule as it's written. So I'm going to bring the 2 down to the front, lower the power to 1, and then leave the x plus 1 alone. Then I'm going to leave the x minus 2 squared alone and do the derivative of x plus 1, which ends up being 1. All right, so there we go. Here we have our first derivative here. Okay, now this is going to be a quadratic polynomial, meaning it's going to have 2 zeros. And there aren't going to be any points where this is undefined because it's a polynomial. Now, one place where we can see some zeros right away is this x minus 2. If we were to plug in x equals 2 in for both of these places, we would get 0 for both of these, which would yield 0. So x equals 2 is going to be a critical point. All right, now I'm going to divide away both sides by x minus 2. So I have 2 times x plus 1 plus x minus 2. All right, so I'm going to distribute here. 2x plus 2 plus x minus 2 is 0. All right, and then that looks to me like we have 3x equals 0, so x is 0. So it seems like our critical points are going to be 0 and 2. All right, now what we're going to do is we're going to do the first derivative test, not only to find our mins and maxes, but we can also use this number line to see where our function is increasing and decreasing. So we plot our critical points on here, and then we plug in different values in between each of these into our derivative to see whether we have something positive or negative. All right, so I guess I'll plug in, say, -1 into this. If I plug in -1, this part will be 0. And then I have -1 minus 2 is -3. Square that to get 9. Remember, we don't care about the actual value. We just care that it's positive. All right, I could plug in now something between 0 and 2. Let's say 1. This is actually always going to be positive. So we really just need to look at this part here. So we have 2 times -1 times 2, so that ends up giving us -4. Then we have 1 minus 2 is -1 squared. So -4 and 1 will be -3. And then finally, if I plug in something like 3, we have positives all around, so it's going to be positive. Another way to fill in this chart is to only check the 1 back here, and then note that since this is a polynomial with distinct non-repeated roots, it's going to change sign every time we pass over a root. So that's another way of doing this without having to plug numbers in here. But regardless, we see that our function, we see that our function is increasing on the interval -infinity to 0. And then it's also increasing from 2 to infinity, which is disjoint in this interval. So the way we express that is we put a union symbol, which looks like a U, and then we have 2 to infinity. Then we know that our function is decreasing where its derivative is negative, and that's on the interval 0 to 2. Furthermore, by the first derivative test, we know that we're increasing here and decreasing here. So it turns out that 0 will be a local maximum for our function, and 2 will be a local minimum for our function. All right, so we have that all set. So let's go ahead and move on to the third step. where we find our second derivative here. Okay, so what I'm going to do is I'm going to do the product rule here. So I have 2, I do the derivative of this, leaving x plus 1. And then I leave this alone, do the derivative of x plus 1. And then I could do the chain rule back here. All right, so this ends up giving me 2x plus 2 plus 2x minus 4 plus 2x minus 4. Remember, I want all of this to be 0. All right, so this ends up giving me 6x equals, let's see, 2 minus 4 is negative 6. So 6x minus 6 equals 0. So it seems like we end up getting x equals 1 as a place where our second derivative is going to be 0. So what's going to happen now? Well, remember that we're not necessarily an inflection point just because we make the second derivative 0. We need the sign to change over that as well. All right, so let's draw our sign chart here. Put x equals 1 there. If I were to plug in 0 to 6x minus 6, I would get negative 6. So it would be negative here. And then if I plug in, say, 2, I would get a positive value. So I know my second derivative is going from negative to positive. So it turns out that 1 actually is going to be an inflection point. I also know I'm going to be concave down on the interval negative infinity to 1, and I'm going to be concave up on the interval from 1 to infinity. All right, so we found all we can from the second derivative. Let's move on to step 4, where we combine the information that we found so far into a number line. So here we go. Here's our number line. And we're going to put all of the numbers that we've gotten so far. So we've had 0 and 2 on the first derivative number line and 1 on the second. So we're going to put all of that here. And then what we're going to do is we're sort of smashing together the 2 number lines that we've gotten so far. So if we return here, it goes plus minus plus between 0 and 2. So before 0, it was positive. It's going to be negative in between here, and then it's going to be positive there afterwards. All right, with f double prime, it's going to be negative before 1 and positive afterwards. We have minus, minus, and then plus, plus. Okay, now we wrote our chart here, but what does this mean? What do these combination of signs mean? Well, it turns out that each one of these has a certain curve shape associated with it. And these are given in this chart. This will be the f prime, and then vertical will be f double prime. So we're going to have 4 combinations. If f prime is positive and f double prime is positive, that means we're concave up and increasing, meaning we're going to look something like this. If we're decreasing but we're concave up, that means we need to look something like this. If we're increasing but concave down, it will look like this. And if we're both decreasing and concave down, then we're going to end up looking like this right here. So these are the 4 basic shapes, and we're going to connect our points on our graph with shapes that look like this. And when we do so, our graph will look remarkably close to the actual, like it'll just be a good graph. All right, so let's move on to step 5 here. Let's begin plotting our important points. So we had important points at 0, 1, and 2. All right, so the function that we're graphing is x minus 2 squared times x plus 1. All right, so f of 0, if we recall earlier, 0 was a local max. So if I were to plug 0 into here, I end up getting 4. So we'll say that's going to be up here at 4. At 1, what do we have going on at 1? If I plug in 1, I'm going to end up getting 2. Remember that this was an inflection point. This was a max. And then at 2, I get 0 for that. This was supposed to be a local minimum. All right, so we have our important points plotted on the graph. Now let's go ahead and fill in and connect these points together. So before 0, for negative numbers, we're going to be increasing but concave down. So according to this, we're going to have a curve that looks like that. All right, so let's draw something coming in like this. And it's a local max, so we know we need to be flat here at the top because our derivative was 0. Next, when we're in between 0 and 1, we're going to be negative for both, which means we're concave down and decreasing. We're going to be going down like this. Then, when we hit the inflection point between 1 and 2, we're going to be decreasing and concave up. That's going to have us do this shape here. We're going to be flat here because this is a local minimum. And then finally, after 2, we're going to have plus for both of these. So we're going to be increasing and concave up. And we know that the end behavior, as we go to the left, we're going to go to negative infinity. As we go to the right, we're going to go to positive infinity. So that's how we finish off the tails of this graph. And there we go. That's it. So we were able to draw a graph of this polynomial right here. And even though each function is going to be different, the steps we're going to do to graph it will be the same every single time. These are going to work for any function that we can throw at you here. All right, let's do maybe 2 more examples here. All right, let's take a look at the function 2x plus 3 divided by the square root of 1 minus x squared. All right, now unlike the previous function, which was a polynomial, this function is actually going to have a limited domain, because if we get below -1 or above +1, then we're going to have a negative under the square root, and that will be a problem. So the domain of our function is going to be limited from -1 to 1. So if we ever get any critical points or inflection points that lie outside of that, we're going to ignore those because we can only draw the graph here. All right, so let's go ahead with step 1 here. Let's look for any asymptotes that we're going to have. All right, well, we could have some asymptotes at plus or minus 1 because that would make the denominator here be 0. So we are going to have vertical asymptotes at x equals plus or minus 1. So on the very boundary of the domain for this curve, it's going to shoot up towards infinity on either side. We're going to have these kind of 2 walls of vertical asymptotes. They make the denominator 0. All right, so those are the vertical asymptotes. And then we don't have any horizontal asymptotes or end behavior because our domain is restricted. So we can't go off to infinity. So it wouldn't make sense to take that limit for this. So we're only going to have these vertical asymptotes. All right, next, let's begin finding our critical points and where we're increasing or decreasing. All right, I'm going to need to do the quotient rule here. So I square the bottom, bring the original bottom up here, do the derivative of the top, which is 2. Then I subtract, leave 2x plus 3 alone, and then do the derivative of square root of 1 minus x squared, which will be 1 over 2 root 1 minus x squared, and then we multiply by the derivative in here, which we will write as negative 2x. All right, now there's that, but we definitely want to clean this up a bit. So we're going to cross out the 2's here. This will become positive. And another thing I'm going to do, since I have a compound fraction here, I'm going to multiply the entire numerator and denominator by root 1 minus x squared. So when I do this, I have root 1 minus x squared times root 1 minus x squared will be 1 minus x squared times 2. And then here, I'm going to have x times 2x plus 3. And then these will cancel here. Meanwhile, in the denominator, I'm going to have 1 minus x squared to the 3 halves, because this was 1 minus x squared to the first power times an additional 1/2 power. All right, oops, this 2 looks like a square. It's not, it's a coefficient. All right, so now, if we were to FOIL all of this out and combine, we end up with 3x plus 2 over 1 minus x squared to the 3 halves. We have a negative 2x squared here and a positive 2x squared here, so those will cancel. So we really only get this. All right, there we go. There's our derivative. And this is a time where we especially want to simplify, because I don't know about you, but I would find it very difficult to tell what's going on with my derivative looking at it this way, as opposed to looking at its simplified version. Right here. So simplification is going to help us a lot in these problems. All right, now it's time to look for our critical points. Now, we see that the derivative would be undefined at plus or minus 1, but those are not going to be in the domain of our function. So we're going to ignore those critical points. Instead, we're just going to see where this is equal to 0. Now, a fraction is equal to 0 only if its numerator is. So 3x plus 2 equaling 0 means that x equals negative 2/3 will end up being a critical point here. All right, that's going to be our only one. So let's go ahead and draw our number line. We have negative 2/3. Let's go ahead and plug in something less than negative 2/3, like say negative, well, I guess negative 1 would be a problem here. Maybe like negative 3/4. That would end up giving us something negative. And then if we plug in something bigger than negative 2/3, like 0, we're going to have something positive. So since we're decreasing and then we're increasing, this means that we're going to have a local minimum at x equals negative 2/3. Furthermore, we're decreasing from negative infinity to negative 2/3, and we're increasing from negative 2/3 onwards. All right, so it looks like we've learned everything we could from the first derivative. So let's move on to step 3, where we test the second derivative, and we find out what we can from that. All right. So I'm going to, another reason why we want to simplify is it's much easier to take the derivative of this as opposed to this mess up there. All right, so I'm going to do my second derivative. All right, let's see. So again, I'm going to square the bottom, giving me 1 minus x squared cubed. Then I'm going to bring my bottom up to the top. And I'm going to do the derivative of the top, which is 3. I then subtract, leave 3x plus 2 alone, and then do the derivative of 1 minus x squared to the 3 halves, which will end up being 3 halves, 1 minus x squared to the 1/2, and then times the negative 2x, which is the derivative of the inside. All right, so once again, we have a complicated looking derivative, but fortunately, we're going to be able to simplify it just like this. So the first thing I notice here is that I have at least a 1 minus x squared to the 1/2 in every single term here. So what I could do is I could cancel all of that out. So if I get rid of 1/2 power here, I'm going to have 3 and then 1 minus x squared. I'm going to cancel these negatives. I'm going to cancel these 2's. And then here, I'm going to have 3 times 3x plus 2 times x. And then finally, in my denominator, if I take away 1/2 power from 3, I'm going to have 5/2 power. All right, there we go. Okay, Next, let's go ahead and FOIL everything on the top and then combine. So we have 3 minus 3x squared plus 9x plus 9x squared, excuse me, plus 6x. All right, so this is going to give us in total 6x squared plus 6x plus 3, all divided by this 1 minus x squared to the 3 halves. All right, that's about as nice as we're going to be able to get our second derivative. I suppose we could factor out a 3 if we'd like, but that's not too big of a deal. All right, now for our inflection points, we're looking for where this is going to be undefined or 0. And once again, plus or minus 1 would make this undefined, but those aren't in the domain of our function. So we're really just looking to see where this is equal to 0, just like the last part. So we have 6x squared plus 6x plus 3 has to be 0. I guess I'll take the time here to divide by 3. All right, and then looking at this, let's see here. I think I'm going to need to use the quadratic formula for this one. We have x is going to be negative b, so negative 2, plus or minus the square root of b squared, so 4, minus 4 times a times c, so 8, all over 2a. All right, and here we end up seeing that we're going to get an imaginary number here. So this means that no real x value is going to make this be equal to 0. So that means that for this graph, we're actually going to have no inflection points whatsoever, because inflection points can only happen if your second derivative is 0 or undefined. So this is a case where we don't have inflection points. Now, what this means is that our second derivative will be the same sign for all real numbers. So if we plug in any number we want, well, I guess in the domain, like 0, we're going to get something positive. So what this is saying is that this curve will always be concave up throughout the whole domain. All righty. Next, we're going to synthesize our information. So remember, we have one critical point, no inflection point, so this will actually be a rather dull number line. Just going to have negative 2/3 on here. And as we learned earlier, f prime is negative before negative 2/3, positive afterwards. And f double prime is just positive everywhere. All right, so this gives us right here, this tells us what kind of shapes we're going to be connecting our important points. All right, let's move to the final part of this where we actually graph. So this will be steps 5 and 6 here. Get our graph set up. -1 to 1. All right, here are our vertical asymptotes. And as we approach them, all right, wait, actually, before I say that, and then we have negative 2/3, which is right here. And this is where we have our local minimum. Remember, the function that we're graphing is 2x plus 3 over the square root of 1 minus x squared. So if we want to see where this local minimum occurs, we plug in negative 2/3. So we end up getting negative 4/3 plus 3 over the square root of 1 minus 4/9. So let's see here. We're going to end up with 5/3 over the square root of 5 over 9. And if we simplify this, I'll save you the details, we end up with root 5. So root 5 is a little bit bigger than 2. So let's put that right here. All right, so what's going to happen then is we're going to be decreasing and concave up. So if we look at the picture that we drew earlier, that's going to be like this. And this makes sense because we're coming down from our asymptote up here. We're going to be coming down like that. Then after negative 2/3, we're just going to be going up and concave up. We're going to be increasing and going concave up. That's going to be going like this. All right, and then there's our graph. So we have this kind of rounded check mark as our graph right here. All right, let's go ahead and do one more example here. All right, so in this example, we're trying to graph the function x squared e to the negative x. Okay, first, let's talk about asymptotes. So this is a polynomial times an exponential function, so it's not undefined anywhere, so we don't have to worry about vertical asymptotes. Now with horizontal asymptotes, let's see. We have the limit as x goes to infinity of x squared e to the negative x. All right, well, on the one hand, x is going to infinity, but on the other hand, e to the negative infinity is going to be 0. So this is actually an infinity times 0 indeterminate form. This is why we have L'Hopital's rules lesson right before this one. So how do we deal with this? Well, the way we learned it in the L'Hopital rule lesson is we move something to the denominator. So I'm going to rewrite this in this form, and then we have an infinity over infinity limit, which means that using L'Hopital's rule allows us to change the limit to be 2x over e to the x. But this again is an infinity over infinity limit, so we use L'Hopital's rule again, giving us 2 over e to the x. All right, now e to the x obviously remains unchanged under differentiation, but polynomials gradually reduce in degree until we have this constant 2 here. Now, as x gets large, this will get very large, and this will remain as 2. So this limit will be 0. And this means that we have a horizontal asymptote this time. This curve will trail off towards 0. All right, now let's check the limit as x goes to negative infinity, because sometimes we can get a different horizontal asymptote by looking in the other direction. All right, now this time we have this going to positive infinity because we're squaring it. But then this is also going to positive infinity. We have e and then going to positive infinity. This one's just going to be positive infinity. So we have one horizontal asymptote, and then we're going off to positive infinity as we move further to the left. So our horizontal asymptote is y equals 0. All right, we found our asymptotes. Next, let's find our critical points. We need to compute f prime of x. The derivative of this right here, we need to use the product rule for. So the derivative of x squared will be 2x. I leave my e to the negative x alone. Then the derivative of e to the negative x is negative e to the negative x. And I leave the x squared alone. So here's our derivative right here. Now, as before, I'm going to simplify this so this is to our advantage. It makes things a lot clearer. So I'm going to factor out that e to the negative x there. All right, so I'm looking for critical points where our derivative is undefined or 0. Now, again, this is an exponential times a polynomial, not going to be undefined, but it could very well be 0. Exponential functions are never 0, so that leaves this. Maybe this right here is going to be 0. 2x minus x squared equals 0. Well, one clear solution to this is x equals 0. So if I put 0 in for both of these, I'm going to get 0. Then if I divide both sides by x, I have 2 minus x is 0, so x equals 2. So these right here, these are my critical points at 0 and 2. All right, now that we found our critical points, let's make our number line. All right, let's plot before f prime, or sorry, before 0. If I plug in, say, -1 into here, I have -2 minus -1 squared, so that'll be negative. I'm going to plug in 1 into here and get something positive, and then I'm going to plug, say, 3 into here, and I'm going to get something negative. And notice that this is positive the whole time. And once again, we have a polynomial with distinct non-repeated roots, so we know that this sign chart is going to alternate every single time. All right. Now, since we're decreasing and increasing, this reveals that 0 is a local minimum, and we're increasing to decreasing, this will be a local maximum. So we found our extrema, and we also see that we're going to be decreasing before 0, increasing in the middle here, and then decreasing afterwards. All right, so we've learned about the function via f prime. Let's go ahead and find out about the function via f double prime. All right, I'm going to do the product rule on this now. So I do the derivative of the polynomial, which is 2 minus 2x, leave the exponential part alone, and then I leave the polynomial alone, do the derivative of the exponential function here, and the negative will pop out to the front. All right, and just like before, we can simplify this by factoring out e to the negative x. So we have 2 minus 2x plus x squared. Don't forget about these double negatives here. We have x squared minus 4x plus 2. All right, so this is going to be our second derivative. Now, once again, it's not going to be undefined anywhere because of the nature of these functions, but it could very well be 0 if this polynomial is 0. All right. Now, looking at this, I don't think this is going to factor nicely, so let's use the quadratic formula here. We have negative b, so 4, plus or minus the square root of b squared, so 16, minus 4 times a times c, which is 8, all divided by 2a. All right, let's see. 16 minus 8 is 8. And then the square root of 8 is actually 2 root 2. So this is 4 plus or minus 2 root 2. And then both of these are divisible by 2. So we end up with 2 plus or minus root 2. And these make this function be 0 right here. All right, so let's go ahead and take a look at this on our number line. Okay, so we have 2 minus root 2, and then 2 plus root 2. All right, 2 minus root 2 is just a little bit bigger than 0, so why don't we plug in 0 for this? If we plug in the 0 here, we're going to get something positive. All right, now these numbers are a bit awkward, so I'm going to use the fact that once again, we have distinct real roots. We have 2 plus root 2 and 2 minus root 2. So I know that my sign chart is going to alternate all the way through. So there we go. We have our sign chart, and we also know that we have 2 inflection points. We have one here, and we have one here, 2 plus root 2. All right, so we've learned about the concavity of our function, and we've learned where it's increasing and decreasing. So now we can synthesize this information into a single number line. Okay, let's label all of our points. So we have 0. A little after that, we have 2 minus root 2. We have 2, and then we have 2 plus root 2. All right, now let's look at what we have here. So for f prime, before 0, it's going to be negative. Between 0 and 2, it will be positive, so plus there, and then it'll be negative there afterwards, negative and negative. Now with f double prime, it's going to be positive before 2 minus root 2, so we have plus right there. In between these radical roots, we're going to have minus, and then there afterwards we'll have plus. All right, so there is our combined sign chart, and this will give us the shape with which we need to connect the important points of our graph. All right, now let's go ahead and draw our graph here. Okay, so recall that the function we were looking at is x squared e to the negative x here. And the important points are all listed right here. So we know that f of 0 will be, well, 0. We're going to have f of 2 minus root 2. It'll be 2 minus root 2 squared e to the root 2 minus 2. We're going to have f of 2, which is 4e to the negative 2. And then we're going to have f of 2 plus root 2, which will be 2 plus root 2 e to the negative 2 minus root 2. All right. So let's go ahead and label our these points on our number lines. We have 0 here. Let's see. This number is about a half. So this will be a quarter. And then we have e to the negative 1/2. So this will be a relatively small number. Let's say it's right there. All right. Then we're going to go all the way to 2, where we have 4e to the negative 2, which is around the same value right here. Remember that 2 is going to be, actually, it should be a little bit higher because it's going to be a local maximum. Then after 2, we're going to go down a bit to 2 plus root 2, the point we have here. And then we're actually going to level off towards the vertical asymptote, or sorry, the horizontal asymptote. Because remember, there's a horizontal asymptote at y equals 0. All right. So let's go ahead and begin drawing our graph here. Before 0, we know we're decreasing, but we're concave up. So let me have the 4 shapes here to remind us. We're decreasing and concave up, meaning we're looking like this right here. And that makes sense because we saw as x goes out to negative infinity, we're going to go to infinity. There's the first leg of our graph, and we know that f prime is 0 here. Then between 0 and 2 minus root 2, we're plus and plus, so we're going to look like this. Kind of go up towards this right here. Then after this, we're going to be increasing, but we're concave down, because this was the inflection point. We're going to come to our local maximum here at 2. Then we have minus minus, so we're going to go down like this. And then after that, we're going to be minus plus. So we're going to look like this. And this is kind of swooping down towards our horizontal asymptote. So what does this function look like? It ends up looking like almost kind of like a parabola or an exponential function on this side. And then we have this bump, and then it's going to level off towards 0. All right, so that's about it for graphing functions. This is definitely something you want to practice as much as you can, because in addition to giving you the practice actually graphing the function, it also gives you a lot of practice finding inflection points, critical points, local mins and maxes, and where we're increasing and decreasing. So there's a lot to be gained from doing these types of problems. All right, I will see you all in the next lesson.